Okay, so here's this snow on the mountaintop, and we have snow. The volume of snow is a function of how much time has gone by and what elevation on the mountain you're at. Okay, and so this then is a rate of change function. And I think I should have been better off calling it R sub S of T and E. So what I'm showing you here is the rate of change of volume of snow with respect to both independent variables, with respect to hours that have gone by and 1,000 feet of elevation. So here's a contour plot of that rate of change function. And we said that we can find amounts of snow fallen. That's the idea of accumulation from rate, right? Accumulation from rate. And how, in general, what's the key thing that allows us to find accumulation from rate? How is it we're able to get an amount of accumulation of a quantity if we have its rate of change? Okay, so that's kind of the end of it. Where does it start? Like how do we? So we're kind of there at the starting block. What's that? Okay, so yeah, so Riemann sum kind of implies more of a geometry, but that's the idea, right? So what is it? So we're going to sum up what little bits of accumulation to get a net accumulation, total accumulation, and how are we able to get a little bit of accumulation? Yeah, so we're totally dependent on constant rate of change, right? We need constant rate of change times a little bit of change of our independent variable, and that'll give us a little bit of accumulation. But this is a totally fluctuating rate everywhere you go. As soon as you move from any spot on this contour plot, the rate is different. So it's not constant at all. So that's why we kind of have to rethink this rate of change into, can we think of it as lots of constant rates? Okay, lots of constant rates. And then we can get a little bit of, let's say a little bit of accumulation, say dz equals some constant rate. And what will it be? Times, so before we said dy equals mdx. This is like the heartbeat of integration, right? Because it calculates a little bit of accumulation for us at a constant rate. But what will it be now? dz equals m times, so constant rate times what? dt de, right? Because this rate now is the rate per both independent variables, volume per hour per 1,000 feet. Okay, so it's the same principle. We need to get constant rates. But now, instead of multiplying by a little change in one independent variable, we got to multiply by a little change in two independent variables. And this will get us a little bit. So given that m is a constant rate, we can get a little bit of accumulation. And then how can we get like a total amount of accumulation? Before that even. So we're going to look at the example here. We're going to look from 1.6 to 2 and from 5 to 6. So let's look at from 1.6 hours to 2 hours, between 5,000 feet up and 6,000 feet up on the mountain. And we want to get some kind of estimate for what volume of snow fell in that time at that elevation range. So what's going to be the strategy here? Is the rate constant through there? No, it's totally changing rate, right? So we're gonna have to kind of split this thing up, just like we did. What do we do in calculus? We took the axis and we split it up into delta x intervals. And what do we do for each delta x interval? You guys seem really tired. So spring break means that you rested and you come back all fired up. No? Okay. All right. Okay. So Right, so we broke up delta x intervals to do what with the rate function? In each delta x interval, we assumed a constant rate instead of the changing rate. So now breaking up, instead of breaking up the intervals and the delta x intervals, we're breaking up like a region, right? A region of our independent variables into instead of intervals into like little squares or rectangles. Okay, so we're going to use 4 little rectangles, and we want to have some kind of way of devising a constant rate for each one, right? A constant rate of change for each one. And so one strategy we did last time was we just kind of eyeballed and tried to find the average rate in the whole rectangle. But something more systematic than that would be to say, let's just pick the rate at the corners. Like we could use let's do lower right corners. So in this first square here, what's the rate at the lower right corner? Or in other words, right there. No, the rate of change. The rate of change. I haven't heard it yet. 1.6. It's on the contour line. It's that corner goes right through the contour line, 1.6. So we got the rate of change of 1.6 right there. We're going to assume a constant rate of 1.6 for this whole square. So we're using the lower right corner, and we're going to do that whole square right there. So we're going to assume 1.6 for this whole square, if we use the lower right corner approach. Okay? What about so this square over here? What about here? Yeah, just say 1.8. We're just estimating anyway, even though that one doesn't go right through the corner. So we'll do 1.8 here. Okay, how about the one above? So pretty close to 2.0, maybe, yeah, 2.0 is close enough. So 2. And then what about this one? 1.8 again. So it's kind of, can we do 1.9? It's kind of in between, right? See that it would be like 1.9? So we've got now for those 4 regions, we've got constant rates 1.6, 1.8, 1.9, and 2. And now we want to estimate the amount of snow. Right? So we're going to do constant rate times dt dE, constant rate times dt dE, etc. Okay, so we're going to do 1.6. What's dt? Change in time. 0.4 was the whole thing, right? So for each little square is 0.2 hours. And then dE. What's dE? Again, 1 is the whole square, so 0.5 thousand feet, or 500 feet. But we want to keep it in 1,000 feet because that's what this rate is in. This rate is in per 1,000 feet, so this has to be per 1,000 feet too. So I think all the squares are going to have this dt dE, right? And what is that, 0.01? Is that 0.01? 0.2 times 0.5? Or is that just 0.1? 0.1. Okay, 0.1. All right, so our dt times te for all these is just going to be 0.1. So we're going to do 1.6 times 0.1. And that'll be the little bit of accumulation for this rectangle. Plus 1.8 times 0.1. That's the little accumulation of snow for this. Remember? M dx plus M dx plus M dx. But now it's M times dy dx plus M times dy dx plus M times dy dx. Because we have 2 independent variables. Are you following? Anyone got an answer yet? So that's your calculation down here in the lower right corner, which is going to get you that accumulated snow between 1.6 and 2 hours from 5,000 to 6,000 feet on the mountain. A couple people have gotten 0.73. And so it's units cubed, whatever it is. Some volume. Some volume. So that's that's not exact, right? That's estimate based on how we estimated how we estimated the constant rates, right? So how would we represent then? How would we represent that exactly? How would we represent that amount of snowfall exactly? So this is our estimate based on a sum of bits of accumulation with constant rates. How do we want to show that or represent that exactly then? So then the exact accumulated volume of snow over that time frame, over that elevation range would be? Oh, we know you just use function notation. Yeah, just use just R sub s. So based on R sub s, we're going to have, say it can be two integrals, right? Two integrals, R sub s, te, dt, de, and that would be, so dt is from 1.6 to 2, and de was 5 to 6. So there we have, that would represent the exact accumulation of the volume of snow that we estimated at 0.73 units cubed. Okay, so in terms of now, we'll do some examples definitely today of if we actually want to crank out a number, then we would need this function. But what's going to happen is we're going to work our way inside out. We're going to take the antiderivative of this with respect to t. What does that mean for e? Yeah, it's just like partial derivatives, right? So, but now we're doing partial antiderivative. When you take the antiderivative with respect to t only, then all the e's are just considered constants. So you would do the same thing with any variable e that you would do with a constant when you take the antiderivative. Then you're going to evaluate that antiderivative from 1.6 to 2, plugged in for the t values, and then you're going to have a single integral with respect to e. All the t's will be gone, and you have a single integral with respect to e, and you'll do the antiderivative and evaluate from 5 to 6. And you get a number, and that number will be something close, hopefully something close to 0.73. But we don't have the function, so we can only represent it. We can only go this far. We don't have this. Well, actually, I do, but it's awful, right? It's this terrible, ugly, horrible function that we don't want to try the antiderivative of. It's a product of exponential functions and trig functions together. Okay, but so representing it is half the battle, setting that up, and we'll definitely do examples of solving those. Questions on the premise here of a double integral, the premise of a double integral? Yeah.
Are we going to do triple integrals?
Yes, we're going to do triple integrals, yes. Again, this is still, everything we're doing is building blocks. Everything we're doing is building blocks for when we get to vector calculus. Vector calculus is going to use maybe 80% of everything we've done up to that point, certainly for sure double integrals. And vector calculus means striving for fundamental theorem for multivariable functions, fundamental theorems for multivariable and vector functions. So there's something like six versions of fundamental theorem. We're going to go for it. In end of November, we should get there. Okay, questions on the approximate accumulation or the exact representation? Okay, so then another way to think of this. So what was another way to think of integration instead of accumulation given the rate function, right? So that's our primary way of thinking about integration, that it's going to give us the accumulation of a quantity, knowing its rate, right? Knowing its rate of change function. But what was another common way of viewing integrals? area under the curve, right? Area under the curve. We said that's not a profound meaning. That's not a deep meaning, but it is a potential way to apply integrals. So say what's this going to look like then?
Volume under the surface.
Volume under the surface. So if I come over here and I look at this here, this is the x-axis here, and this is the y-axis. So somewhere over here is from 1.6 to 2. Two in red. From 1.6 to 2, and from 5 to 6. So there's that same region from 1.6, x equals 1.6 would be along here, 1.6, right? To 2. And then from 5 to 6 and y is this same rectangle that I carved out. And this double integral then has a geometric meaning, right? Yes, the double integral is the accumulation of this quantity given this multivariable rate function. Yep. But it's also, if we think about what we did, we took area of the base times the z value of the rate. So what is that finding? What is that finding? Area of the base, so dt times de times a z value. What does that find? Volume of like a rectangular column, right? Like a rectangular column whose height is defined by the surface. So I came over here and we chopped it up into 4 pieces. And so when we did this, 1.6 times 0.1, 1.8, we were also really finding these volumes of rectangular columns. So I'll just draw one of them, or else it'll be a total mess. But basically, and we used what? We used the lower right corner. Where's the lower right corner for this first one? Right here, right? So we take the z value on the surface at that point right there, and then let the height of it be that z value, right? So I'm trying to show that this is the actual point on the surface at the lower right corner. So because things are turned in R3, lower right corner is, you see that this, for this first little rectangle right there, that's the lower right corner. Do you see that? Because you'd be looking at it from this way in the xy plane. So the lower right corner would be, lower would be this way, right would be this way. So there's your lower right corner for that tile right there. I'm going to pull the z coordinate off from that lower right corner and make the height of my column the same for all of it. And then we're finding the volume of that column. And the volume of that column is going to be 1.6 times 0.1. And then I'm going to add up those volumes. This is essentially also adding up the volumes of columns to get what? An approximate of volume under this surface, right? Volume under this surface, but over that square region. Okay, so you're really quiet. Is it easy? Are you lost? Do you get it? Questions? Please ask a question if I've lost you. So then the double integral in this so what happens with the double integral? It's like these little tiles get really, really small, right? We get more and more of these tiles. The mesh gets finer and finer. So there's hundreds and thousands of these tiles. And over each tile, we get like the volume of a really skinny column. And when those tiles get skinny enough, the sum of all those volumes of those tiles gives you the actual volume of the of the solid formed when the top is the surface, projected over whatever square region you're talking about. And so then this would then give you also the exact volume. Oh, so this is a different kind of volume, right? So this happened to be, our quantity happened to be volume of snow, which is not, this is not a volume of snow in here, right? Totally different. This is a volume of a geometric volume according to the units on the axes, right? According to an X unit, a Y unit, a Z unit. So those are two different volumes, right? Volume, this is volume, the blue one's volume of snow, which is totally different than volume of adding up these columns and then making them small enough so that you get exact volume under the surface over that square region. Under surface over R. Now what happens if your surface goes negative z's? Then what will a double integral give you? Will it give you volume? For any place in your region where z is dipping underneath the xy plane?
Yeah.
Is it going to give you volume, the double integral? Right, so in order to truly get volume, we have to have a negative or non-negative surface like the one I'm showing you here. But if over your region, your surface dips below the xy plane and carves out volumes underneath, then what will the whole double integral give you? Just like it gave us in Calc 1 when the function went underneath the x-axis. Net volume, right? Or difference of volumes, right? Anything above, any place in the region where the surface is above, it's going to have a positive contribution to the volume, and any place where that surface digs below the xy plane, all that stuff is going to have a negative contribution to the integral. So you're going to have difference of volume. So really, this was only exact volume because our function was always positive. So the most generic way to talk about a double integral in a geometric sense is that's going to give you net volume or difference of volumes. Okay. Okay, so let's do an example with a more simple surface. Any questions on the volume of snow example or where we talked about the geometry of this double integrals? Okay. This one. Okay, so here I'm showing our region is. So I'm going to show the region and the xy plane on the right, and then I'm going to show everything in R3 on the left. Okay. So my region here is from what? From 0 to 4 in x, and 1 to 3 in y. And then I have the surface here. So should I have it? It's just 1 plus x. So let's give this a spin so you can see what's going on here. So I want to talk about what would be the double integral of the function 1 plus x. 1 plus x over this region R. So f of xy equals 1 plus x. That's what we're talking about. So that function could be a rate of change of some quantity with respect to two variables. And then so then we could say the double integral of, so double integral of R over of f of xy dA. So that's a generic way to write the double integral over a region R of some function dA. Okay, and so then we can substitute everything in. So what is our function? 1 plus x. Okay, and so with these rectangular regions, everything's interchangeable. Okay, you can do x first or y first. It doesn't matter. So we'll just do x first, right? So dx. And if we're doing dx, then x goes from 0 to 4. And dy from 1 to 3. So in a quantity accumulation, so in an accumulation context, I want you to tell the person next to you, have a discussion. What exactly would this find if we're talking about the context of accumulation and rate of change? So, and what are all the details? So, what's the meaning of that expression? What would it find? What do all the parts mean? Okay, in the context of accumulation. Go talk. Everybody's talking about. Did everyone get a blue sheet in the back? Okay, what do we think? So, what is the interpretation of this double integral if we're talking in the context of accumulation and rate of change? Kyle, you want to try?
I guess I could try. I'm not really sure how to word it.
Okay.
I think it's kind of like almost looking at just a vertical surface with just an area along the x-axis, and then when you take the portion of y, it turns it into a volume.
Okay, that's more like the geometric interpretation. So, what about in terms of accumulation and rate of change? In terms of accumulation and rate of change, what does this thing find? Paige, you want to try?
Sure. I don't exactly either, but so if f of x y was like if that function was like a rate of change of something,
Right.
then the double integral would be the accumulated like volume or whatever it is that is changing.
Okay. Right. So the 1 plus x is, in the accumulation rate of change context, 1 plus x is the rate of change function with respect to both x and y. Both x and y, right? It's going to be like some quantity per change in x per change in y. Okay? And then, so then this, she said the double integral then was going to calculate. What will it calculate then? Total change, net accumulation, if what happens? So total change and net accumulation if what? So specifically, if x changes from 0 to 4 and y changes from 1 to 3, right? So we're talking about over this, for these values of x and y taken together, right? For those values, the region of those taken together, we'll get the net accumulation. What will it mean for a geometric context? Sneezing, yawning. Woof. You guys are a loud lot. What's that? total volume. And it, will it be total volume in this case?
Yes, it's above.
Okay. And total volume of what, Ezra?
The total volume of the shape or whatever in that space that's provided. It's kind of
So,
a wedge.
okay, it's a wedge.
The volume of the wedge that is.
It's the volume what? Beneath the surface, down to the XY plane, but just the part of the surface that's over the region, right? So let's draw it. So maybe like this. Is everything showing up? Oh, I was doing so good. No, is that right? Does that look right? Something's wrong at the top.
It needs to be steeper, but it's generally so you're fine.
Are these supposed to be parallel to the?
Yeah.
I like my drawings. Don't like messing it up. This? Better. Okay. Yeah, so it's this wedge thing, right? Okay, so it's either some accumulated amount given the rate of change as x and y vary over this region, or is the volume of that thing. So we're going to find it both ways, right? So we should be able to use calculus to get that value, and then we should be able to just use geometry because this is an easy enough solid that we can just use geometry to find it and confirm that we did it both ways correctly. So what do you want to do first, geometry or calculus? Calculus here. Okay, calculus. So calculus means we're going to work inside out, and we're going to start with this one here, and we're going to take the integral with respect to x. Anytime there's any y's in there, we're just going to treat them as just like constants. So if y's are multiplied by x's, what happens to those y's? Bring them along, right? Bring them along for the ride. If there's just y's sitting by themselves, or expressions of y by themselves, and we're integrating, what's going to happen? They're going to get an x. We're going to hold on to them. They're going to get an x when we do antiderivative, right? But we don't have any y's here, so we don't have to worry about that. So antiderivative is going to be?
X plus x.
So we're going to hold on to the 1 and the 3 here. And we're going to do what? X plus x squared over 2 and evaluate that whole thing from 0 to 4. And then once we get done with that, then we'll do dy. Is it okay? Is that 12? All right, so I'm hearing that that's 12. That's a nice streamline. So 1 to 3 of 12 dy. 12y from 1 to 3. Is that 24? So if this were accumulation rate of change, it would be 24 quantity units, whatever quantity it is. So meters, it could be meters traveled, it could be milligrams, 24 milligrams of some substance or something like that. Right? It's not a rate of change. Now it's the total accumulation of the quantity, whatever that quantity is. Okay, so over here, we can look at our dimensions. How are we going to find the volume of this thing over here? So this was what? 0 to 4. This is 4 here. And 1 to 3. This is 1 and 3 in y. How are we going to get the volume of this thing? What's going to be the general approach here? Break, yeah.
Could you find the area of one of those vertical trapezoids and then multiply it by the change in y to get the volume?
Okay. Yes, okay, that's good. So that works. You could do a trapezoid, a vertical trapezoid, and then just multiply it by 2. Yeah, that works. Or, Charlie, what'd you say? Yeah, a box and then a triangular solid, right? You see that? So there's the boxes below this, and then a triangular solid, this. All right, so so then we need some z values, right? Here, this is at the point 0, 3 and 0, 1. What is our z value there? 0, 3 and 0, 1. 1, right? Z equals 1 from the function. And then out at x equals 4, what's our z value at x equals 4? Out here, z equals 5, right? 1 plus x. Surface is always 1 plus x. So this bottom block here is going to be, so we could do volume bottom and volume top. Volume of the bottom block is going to be length times width times height. Length is 2, width is 4, height is 1, right? So 2 by 4 by 1. Everyone see that? Volume of the top triangle piece, T for top or T for triangle, it's going to be what? 1/2 so 2 times 4 times this height here, which is another 4. And the 16? Beautiful. And the total? Got it. Questions? Does it make sense? Okay, so the volumes over rectangular regions are really, really convenient. They're convenient because what? All your bounds are just going to be values. And they're totally switchable. We could have done dy first. What would we get? If we did dy first, we'd have y plus xy. Evaluate that from 1 to 3. The y's will be gone. Then we'll do whatever that comes out. And with respect to x from 0 to 4. So it's totally reversible in terms of the order you get. And you just have numerical limits of integration. So really convenient and nice. Any questions on this example? So let's just do, while we're here, let's just do one. There's a harder one from your web work that's due tomorrow. You got a web work due tomorrow night. Let's just do my version of one of those just to see maybe a little harder antiderivative. And then we'll move on to the next thing here. Questions on this example? So, yeah, so one thing about this you have to get used to is we're going to be working in R2 like this with these regions. But then if you drew it in R3, everything's turned 90 degrees. Right? So do you see that this region is exactly the same as this one? X varies from 0 to 4, Y varies from 1 to 3. Okay, so from the web work. I think it's number 9. The one that had the one that had the lowest. So let's do that. Oh, 7. All right, let's do this one together. So you should be able to draw this first of all. You should be able to draw that region if you needed to, and then the surface, not so much. That's a complicated surface. But then you just imagine that you have this surface in R3 over that rectangular region where y goes from 1 to 2 and x goes from 2 to 3. Okay, but if we just want to get the Double integral. So first we're going to integrate with respect to y. And so remember that x it's just like a constant. But this is all to the minus 2. So what will the first antiderivative be? So this whole thing to the minus 2, something plus y. Antiderivative will be 4x plus y to the minus 1. And do we need any factors out here to clean up any mess? Just negative 1 for the exponent, right? If there was like a constant multiple on the y, so now you need all your integration techniques from Calc 2, right? If there's a constant multiple on the y, now we're kind of undoing the chain rule, right? You need to account for that as well. Okay, and we're going to do that antiderivative from 1 to 2. So what do we get? So we plug 2 in, and we're going to get, so we're going to get negative, what, 4x plus 2 to the minus 1. And then minus a minus will be plus 4x plus 1 to the minus 1. Did you catch it? See what I did? I'm evaluating that antiderivative for y. These are y values, right? We were doing it with respect to y first. These are y values. So I'm going to plug 2 in for y, holding on to x like a constant, and then 1 in for y, and I'm going to subtract. Just the way you apply the fundamental theorem of calculus. Okay, then what? So now we've got to do this with respect to x. So what will this antiderivative be with respect to x? Minus 4x plus 2 to the minus 1. All right, so here's the one time when you don't use the power rule. The one time you don't use the power rule when you're taking antiderivative is power is negative 1. If you do, you'll get all kinds of warnings, right? Power becomes 0, and then you have 1 over 0, right? So it's just all kinds of red lights flashing and telling you something's different, something's not right. But any other power besides negative 1, you're going to use the power rule and raise power by 1, okay? But here we're going to do negative, what? Natural log of, now remember, do you remember from Calc 2? You need an absolute value to maintain the domain. It's a domain issue. We want the same domain of our antiderivative that we do have for the original rate function here. And then going to do what? And then do I have the negatives right? Yep. And then plus natural log of x plus 1. And that whole thing evaluated from 2 to 3. So you're going to plug 3 into that whole thing. And then you're going to plug 2 into that whole thing and subtract. Question? Well, maybe. Yeah, definitely. Yeah, you definitely do, right? When you take the derivative of this, a 4 will pop out, a 4 that we don't have. So we need negative what? Thank you. Okay. And also on this one. Again, we're going to plug 3 in to the whole expression. And then plug 2 into the whole expression and then subtract, right? And what is that about? That's about the fact that the net accumulation at this rate is the same as final amount of accumulation minus initial amount of accumulation. You're just doing final minus initial in order to get a net accumulation. Okay, so I'm not going to take the time to type all that in and see if we get the green bar. But again, 3. Don't put 3 in. So here's what students might do: put a 3 in here and 2 in here. No, you put 3 in the whole thing, and then you put 2 in the whole thing, and you subtract. So you're gonna have your answer would actually have 4 natural logs in it, right? Natural log of what is that? 14 over
over 4.
over 4, natural log of 13 over 4, then natural log of 10 over 4, and natural log of 9 over 4. Get the signs right. Make sure you have your signs right. When you subtract with a 2 in there, this will become positive, this will become negative. When you subtract with the 2 in. Questions on that? Okay, so let's move on to away from rectangular regions to what we call general regions. General regions. I made this GC file this morning. I'm very proud of it. Okay, so here's a region. I'll show you why in a second. So this region is not rectangular, right? X varies from, so let's maybe do this. X varies from 0 to 2. But y varies from
2 functions.
x squared, or 1/2 x squared is the bottom function. I'm calling it b of x, up to 4 minus 1/2 x. So the bottom function is 1/2 x squared, and the top is 4 minus 1/2 x. And this is this region that we get when we do that. And so I want to integrate this the surface over that region. So first of all, do you see that it's the same region? That's the same region. Just remember, in R3, things are turned 90 degrees. It's the same. And so really, when we do that, then we're just looking at, all we need is the part of the surface that's over that region. So now all I care about is the part of the function that's over the region. If I look straight down, that's all I see. Okay? Okay, so what will that double integral be? That double integral will be. So this, what we're going to do, we're going to do is what's called a type 1. And this language is just for us to communicate. A type 1 is where you're gonna start by going bottom to top, then left to right. Now this is all, these bottom, top, left, right are all in the context of the R2 point, right? Looking at the R2, the thing on the graph on the right side. So what is the bottom of it? No, the bottom is not 0, right? The bottom is our 1/2 x squared. And our top is 4 minus 1/2 x. Okay, so bottom to top is what? dy first. And then dx last. This is what we mean by type 1 integral. Bottom to top, then left to right. Bottom to top, then left to right. So our integral, double integral will be. And so when we say first and last, which integral is first?
The dy.
Right, the dy is first, but then in the double integral, which is first? So with these double integrals, you work inside out, right? Inside out. So the inside integral is the dy, the first one. So we're going to go from what to what? We go from 1 half x squared to 4 minus a half x. Our function is 2 plus 0.6 sine x, or cosine x sine y. I hope this doesn't get too ugly. I don't think it will. Shouldn't be too bad. Yeah, it's going to.
Yeah.
But we can do what we can. We're not gonna do what we can. Just don't freak out. Okay, and then that's which integral? dy. So that's our inside. The inside integral comes first. That's bottom to top, right? Bottom to top. We're talking about 1 half x squared up to 4 minus 1 half x, and then 0 to 2. What I should have done, the problem here is going to be the x squared. That's going to be the problem. So maybe we could, let's just do 1 half x. And then we can make our way to the integral. We can actually get the integral. Okay, so antiderivative with respect to y. So I need some room to work here. So let's turn this one off. So we're going to have 2y plus 0.6 cosine x comes along for the ride times negative cosine y. I agree. From 1 half x to 4 minus a half x. And then we're going to do that thing. We're going to integrate from 0 to 2 with respect to x. So we're going to do 2 times 4 minus a half x plus 0.6 cosine x times negative cosine of 4 minus a half x. Is that good? That's the first part. Minus 2 times 1 half x plus 0.6 cosine x negative cosine of 1 half x dx. So there's another issue besides just the x squared, and that's now cosines with different arguments. So we're going to stop there on this problem. Okay. So yeah, cosine x times cosine with another argument is not something within our basic techniques that we can do antiderivative of. But we could put it in technology and have it actually find it if we want. But so then what would we do now? So then typically at this point you'd have a doable x integral and you just finish, right? The calc 1 integral. And what would that give us? This would give us
volume or the total.
yeah. So either an amount of accumulation given that rate function, or the volume of this with a trapezoidal base up to this curved surface, right? Everything below the gold down to the pink. Everything below the gold down to the pink would be the volume of that. Okay, so let's have you try something easier. Or actually, let's do an easier one together here. Okay, any questions on that example? So let's do, here's a good one. So we'll do from, all right, so we got some surface here. And I guess I got to start at 1 here. So this is y equals ln x. And then x equals 1, and x equals 2. So that's the same thing there. So we want to set up the type 1 integral. And then this is just any generic function f. We're not going to solve it, okay? So this is just a generic function f. So type 1 would be, can you for your notes, can you try writing the type 1 here? Write the type 1 integral for integrating the surface f over this region here. Can you write out what the double integral would be?
So integrating dx gives you a different value.
Where's my pen? For the integral? No. It's a good thing. All right, let's see. William, did you get it?
Yeah, I got from 1 to 2,
Okay.
and then from 0 to natural log x,
Right.
fxy, and then dy dx.
Do you get the limits right? You get the order right? Nailed it. Okay, nailed it. Good. So, and that would be geometrically, it'd be what? The volume under f down to the xy plane over that purple region. Or what? If f curves underneath the xy plane somewhere in that region, then we're going to get a difference of volumes, right? Difference of volumes. Okay, so now type 2 for our, and again, type 2, this is just our language so we know which one we're talking about. What are we going to do? This is going to be left to right first, left to right, then bottom to top. So left to right is with respect to what first? Dx first. So first dx, then last dy. So can we go from 1 to 2 and 0 to ln of x? Will it work? So can I just flip these? No, because when I go from 1 to 2, what will that really do? This is going to, 1 to 2 is going to go from 1 to 2. All right, and then, so it's not going to work. And then what also is going to happen is we're going to be integrating with respect to x first, and then with respect to y, and in the end, we'll get a function of x, right? We should get a number. So we have to have our function on the inside, our functions on the inside integral, and constants on the outside for this to work. Yeah.
So does that mean we have to end up looking at the graph as if x was like the y-axis, so then we have to look for a function of how x changes in respect to y?
Yeah, so we're exactly right. Exactly. We're going to go from what? Left to right first. So think about starting here from left to right. So this is like a typical strip across our region from left to right. And so what we need is the left side means x, and we need x equals some function of y, x in terms of y. And what is x in terms of y on the left side of this? Right, so it's like the inverse. So if you solve for x, you get e to the y, right? And then what is x over here? What's the right side? X equals? It's just always 2, right? It's always 2. So we're going to go from e to the y on the left to 2. And from what to what? Then we're going to go from bottom to top. So then we're going to take all these these horizontal slices. What's the y value at the bottom of that first horizontal slice? Y equals 0 up to? Yeah, so what we need the y value right there. And he said ln of 2. You see that? So, and then it would be dx dy. So when you do type 2, your inside limits are going to be x as a function of y. And then your outside limits will be constant values of y. It has to be that way. You can't have functions on your outside integral, because then you end up with a expression, you won't get a number. And we know we're going to get a number, which is, in this case, the volume, right? But these two will give the same value. There are two ways to write the exact same, geometrically, the same volume. Or, if f is rate of change, well, you're going to get the same accumulation of your quantity. Because you're still accumulating f over the same region, you're just ordering it different, right? Organizing it differently. So those will be equal. Okay, so